Up to and during most of the 19th century, human medicine was a mixture of fable and prayer at best. For generations, the medical profession was dominated by strange empirical theories and ad hoc medications passed down through the centuries. Average life expectancy in Western countries was below 40 years, dragged down by horrific child mortality rates. Even those who survived childhood could only expect to live into their early 60s. Meanwhile, in the parallel world of fashion, color was dictated by geography and backbreaking labor. For millennia, style was dominated by the king of dyes. Phoenician purple, painstakingly extracted from thousands of crushed sea snails and reserved exclusively for royalty and the filthy rich. There was indigo, harvested from plants across Asia, and centuries later carmine, derived from crushed beetles imported from the Americas. Who could have predicted that these two completely disconnected worlds, high fashion and human survival, would collide? Who could guess that a quest for a rainbow of synthetic colors would lay the bedrock for the multi-billion-dollar pharmaceutical industry that cures diseases, improves our quality of life, and prolongs our time on Earth today? This is the story of how an accidental discovery of a synthetic purple dye triggered a frantic scientific gold rush, maturing the field of organic chemistry until it evolved into the pharmaceutical industry of our civilization. It is an industry that has helped drive average lifespans up to 78.5 years in the USA and between 82 and 84 years across Europe. Welcome to Chemistry Forging Civilizations, where molecules find purpose and chemical reactions shape history. Chemistry, the science of transformations, changed humankind forever. Act 1. A lucky failure, a 19th century high-tech. In the mid-1850s, an 18-year-old chemistry student named William Henry Perkin was dealing with the future. Studying at the Royal College of Chemistry in London, Perkin was given a daunting task by his professor: try to synthesize quinine, a precious natural drug harvested from tree bark and used as the only effective treatment for malaria. Now, you have to understand at this time, structural organic chemistry was practically non-existent. Nobody understood the true geometry of molecules, let alone the real mechanisms of organic reactions. The only data a chemist could determine was the elemental composition, the raw ratio of carbon, hydrogen and nitrogen atoms. Perkin attempted to construct quinine by oxidizing a chemical called allyl toluidine, isolated from coal tar. He mixed it with potassium dichromate in an acidic environment. Potassium dichromate is a medium-high oxidant with a standard electrode potential of E standard equals plus 1.33 volts. Quinine was absolutely not produced in that experiment. Instead, Perkin ended up with a sludge, a dark, sticky, unpromising residue. But when he went to wash his glassware with alcohol, the sludge dissolved, revealing a vibrant, beautiful purple color. By absolute luck, the aniline and toluidine impurities in his coal tar had oxidized into a synthetic, light-fast purple dye that rivaled the Phoenician purple of antiquity. He named it Mauveine. Suddenly, coal tar, a foul-smelling, toxic industrial waste product of the gas lighting era, could be transformed into highly valuable, chemically pure luxury compounds. Perkin had set out to advance the future of medicine. Instead, he found the goose that lays the golden eggs. It made him a wealthy man. By the following year, he had abandoned his studies and established a massive dye works factory. High-tech manufacturing was born. Act 2. Light absorption. What you see is not what you get. To mass produce these synthetic dyes, early chemists realized they desperately needed to understand how molecules interact with light and how they bond to physical substrates like cotton and linen. Remember, at this time the electron hadn't even been discovered yet, nor was there any knowledge of structural organic chemistry. But the pure commercial novelty of synthesizing nature's colors unleashed a massive research frenzy that very soon made fortunes for entrepreneurs like young Perkin himself. So how does a molecule produce color? When white light illuminates a suitable organic molecule, the radiation causes the excitation of an electron, kicking it from its lower normal energy state to a higher energy level. The molecule absorbs a specific slice of the visible light spectrum, and our eyes detect whatever light is left over, the complementary color. We visualize this using a color circle, a diagram of the visible spectrum bent into a wheel. If two colors sit opposite each other on this wheel, combining them creates white light. The complementary rule, a molecule that absorbs light at a wavelength of roughly 520 nanometers, absorbs green light. Because green is removed, our eyes perceive the complementary sensation of deep red. If it absorbs at 460 nanometers blue light, it appears orange-brownish to us. The specific parts of a molecule responsible for this absorption are called chromophores. These are unsaturated groups of atoms containing multiple covalent bonds where atoms share more than one pair of electrons. Act 3. The Dance of the Chromophores. Perkin's accidental discovery ignited an obsession with structural organic chemistry. Chemists wanted to design reactions to produce any color on demand. The first massive breakthrough came 3 years after Perkin's discovery, when Auguste Kekulé proposed his revolutionary theory on the structure of benzene. Because chemists knew that toluene had no structural isomers, Kekulé concluded that benzene consisted of 6 carbon atoms joined in a perfect ring with alternating single and double bonds. Later, critics argued that if Kekulé was right, substituting hydrogen on 2 consecutive carbons should produce 2 distinct configurations depending on where the double bond sat. But experiments proved no such variations existed. The mystery was finally solved 40 years later by Linus Pauling and the advent of quantum chemical theory, which introduced the concept of resonance. In quantum mechanics, resonance doesn't mean the bonds are vibrating back and forth. It means there is a complete delocalization of the pi electrons across the entire 6-carbon ring, spreading the negative charge smoothly and providing immense energetic stability. Why then is pure benzene completely colorless? Because its electrons are held tightly, it absorbs radiation between 180 nanometers and 260 nanometers, which is deep in the ultraviolet region. Our eyes see nothing. But by systematically tinkering with substituents on that aromatic ring, chemists found they could alter the energy gaps. What determines a molecule's color are the specific electron transitions between bonding pi orbitals and anti-bonding pi star orbitals, or between non-bonding n, lone pairs, and anti-bonding orbitals. A color-rendering molecule is known as a chromogen. Within it, the actual chromophores contain those unsaturated bonds. If you chain these double bonds together, a phenomenon called conjugation, like having 2 double bonds separated by a single bond, the energy gap drops. According to Max Planck's fundamental law, E equals Planck constant h times nu, the frequency of the light wave, equals hc over lambda, the wavelength of the light wave. Because the transition energy E decreases, the wavelength L increases, shifting the absorption toward the red end of the spectrum and intensifying the color. Furthermore, if you attach saturated covalently bonded groups containing lone pairs, like amino groups, NH2, hydroxyls, OH, sulfhydryls, SH, or halogens, directly to the chromophore, they interact via conjugation to shift the wavelength further. These auxiliary color-boosting groups are called oxochromes. Act 4. The Chemist's Palette. Armed with this structural theory, late 19th century chemists engineered some of the most spectacular iconic synthetic dyes in history. Methylene blue, built around a flat planar phenothiazine core, a central ring containing sulfur and nitrogen, flanked by two benzene rings, capped with dimethylamino groups. Because the molecule is perfectly flat, it possesses the terrifyingly useful ability to slip cleanly between the stacked base pairs of DNA, a process called intercalation, making it a legendary biological stain. Fuchsine. This deep red dye relies on a central carbon atom bonded to phenyl rings. Two rings carry amino groups, while the third features an altered electron-deficient iminium group, equals NH2+. This creates a modified alternating quinoid structure that absorbs green light with incredible efficiency. Malachite green, a classic textbook example of a resonance hybrid. It features a central carbon bonded to three aromatic rings, two of which are modified with dimethylamino groups, -N open parenthesis C H3 close parenthesis 2. A positive charge flips continuously back and forth between the two nitrogen atoms at opposite ends of the molecule, traveling seamlessly through the central carbon, a resonance structure responsible for the color. Alizarin, a natural dye that chemists successfully synthesized in 1869. It features an anthraquinone core consisting of three fused rings with two ketone oxygens. Alizarin acts as a molecular chameleon based on pH. At a neutral or acidic pH less than or equal to 7, the molecule holds onto its protons and is virtually colorless. But in a basic environment, pH greater than 7, its hydroxyl groups drop their hydrogens, and the resulting anionic form shifts its resonance structure to adopt a brilliant violet-purple hue. Act 5. The Gateways to Modern Medicine. Bonding mechanisms. But how do these dyes actually stick to things? Dyes don't just stain materials uniformly. Their adhesion relies on precise chemical compatibility between the dye molecule and the fiber substrate. Dyes that carry a net positive charge, like fuchsine, malachite green, and methylene blue, are cationic. They bond via simple electrostatic attraction if the fiber provides negative anionic sites. Protein-based fibers like wool and silk are packed with amino acid chains containing carboxylic acid groups, COOH. At the right pH, these groups lose their protons to become negatively charged carboxylate ions, COO, snapping onto the positive dye molecules. It creates an intense color, but one that can eventually fade or wash out. Cotton, however, completely resists this method. Cotton is made of cellulose, a rigid polymer of beta-D-glucose molecules locked together by highly stable glycosidic bonds, offering absolutely no readily ionizable groups. To dye cotton or to make wool dyes permanent, chemists utilize the mordant method, which operates on the sophisticated chemical principle of chelation. A chelate forms when a single molecule possesses two or more donor atoms positioned perfectly in three-dimensional space to grab onto a single central metal ion like a claw. Alizarin is a masterful chelator. It features a carbonyl oxygen, CO, sitting directly adjacent to a hydroxyl group, COH. To dye wool or cotton, chemists would pre-treat the fabric with metal ions like aluminium, Al3+, or iron, Fe2+. The metal coordinates with the amino acids in wool, and when alizarin is added, it clamps onto the metal, creating an incredibly stable alizarin metal fiber bridge that will never wash out. For cotton, which forms weak coordination bonds, chemists added an organic intermediary called tannic acid. Tannic acid is packed with phenolic groups, AR-OH, that anchor tightly to the cotton's cellulose via extensive networks of hydrogen bonds, while simultaneously leaving free coordination sites to bind metal ions, locking the whole complex together. Act 6. Stepping into new territory, staining the invisible. In the early 1870s, a researcher named Carl Weigert made a profound conceptual leap. He realized that if these synthetic dyes bonded with such specificity to biological fibers like wool and silk, they could be used to stain biological tissue under a microscope. He became the first scientist to successfully stain bacteria with synthetic pigments. His brilliant young cousin, Paul Ehrlich, took this observation and fundamentally transformed human civilization. Ehrlich's 1878 doctoral thesis, Contributions to the Theory and Practice of Histological Staining, documented a startling phenomenon. Certain synthetic dyes would selectively bind to and stain invading bacterial cells while leaving surrounding human cells completely untouched. Ehrlich stared through his microscope and arrived at a monumental historical realization. If a dye molecule can be designed to selectively target and stick to a bacterium, we can attach a chemical toxin to that dye. The dye will act as a homing vector, delivering the toxin to kill the pathogen while leaving the human host completely unharmed. This was Ehrlich's magic bullet hypothesis, the intellectual birth of chemotherapy and modern drug design. Chemists realized that the exact same atomic forces making a dye stick to wool could be engineered to make a drug stick to a living pathogen in vivo. If you can design a molecule to bind to a wool fiber protein using ionic and covalent bonds, you can design a synthetic drug to bind to and disable a bacterial enzyme using the exact same physical forces. By 1894, Ehrlich formalized this as the lock and key model, proving that biological drug action requires a strict geometric and spatial compatibility between the synthetic molecule and its biological target. Act 7. Tinkering with the benzene ring, the making of an industry. Suddenly, the organic chemistry labs of Europe stopped looking for colors and started looking for cures. Armed with a new understanding of electrophiles, electron-deficient entities hungry for a negative charge, and nucleophiles, electron-rich species looking to share pairs, chemists began playing a massive substitution game on the benzene ring. They expanded their definitions using Lewis acid-base theory, recognizing that electron pair acceptors and donors were the ultimate keys to organic synthesis. Because benzene has 6 delocalized pi electrons clouding above and below its ring, it behaves as a strong nucleophile. Chemists learned how to exploit this through electrophilic aromatic substitution, replacing hydrogen atoms through nitration, sulfonation, and alkylation. Take the synthesis of aspirin, acetyl salicylic acid, one of the earliest triumphs of the era. Benzene is normally far too stable to react easily, but by introducing an acid catalyst, chemists protonated acetic anhydride, converting it into a ravenous electrophile that the salicylic acid ring could easily attack, creating a mass-producible safe painkiller. To sulfonate a ring, chemists utilized fuming sulfuric acid. a dense solution of sulfur trioxide, SO3, dissolved in pure sulfuric acid. Because oxygen is intensely electronegative, 3.5, compared to sulfur, 2.6, the three oxygens in SO3 yank electron density away from the central sulfur atom, turning it into a powerful electrophile. When benzene attacks the sulfur trioxide, it forms a classic intermediate known as a complex, sigma complex, which exists as a highly reactive zwitterion carrying a positive charge on the carbon ring and a negative charge on the oxygen. Then a bisulfate anion, HSO4-, acts as a base, stripping away a hydrogen proton to restore the ring's stable aromaticity, leaving a sulfonated molecule. Nitration followed an identical logic, using concentrated nitric and sulfuric acids between 60 degrees Celsius to generate a highly reactive nitronium ion, NO2+, electrophile. But the ultimate tool came between 1877 and 1881 with the invention of the Friedel-Crafts reaction. By utilizing a powerful Lewis acid catalyst like aluminum chloride, AlCl3, chemists could rip halogens of alkyl or acyl groups, creating incredibly reactive carbon cations, carbocations. These carbocations could seamlessly attack nucleophilic benzene rings, allowing chemists to link carbon chains together at will. It is a process used to this very day to manufacture everything from aviation fuel to the everyday painkiller ibuprofen. Act 8. The pill and the ultimate synthetic concepts. Diels-Adler reaction and organometallic catalysis. Still, as the industry advanced, the molecules needed to fight complex diseases became highly intricate, requiring specific three-dimensional shapes. Pharmaceutical products, like the pill, owe their appearance to the Diels-Adler reaction and underlying concepts. No, we are not talking about the blue pill of latest decades, but about the pink pill of the 60s. The contraceptive pill that unleashed the sexual revolution of the mid-20th century owes its development to the ability to synthesize complex 3D molecules. Diels-Adler produces stereospecific products of great complexity. Diels-Adler forces a DN, a molecule with two double bonds, and a dienophile, a DNA-loving molecule, to snap together into a six-membered ring. Remarkably, it creates two new carbon-carbon bonds simultaneously and predictably controls the 3D orientation stereochemistry of the resulting molecule. 4 pi electrons from the dien and 2 pi electrons from the dienophile interact to form a new six-membered ring. The reaction forces the creation of two carbon-carbon bonds simultaneously. The most historically significant applications of the Diels-Adler reaction in organic synthesis is its use in the total synthesis of cortisone, developed by Robert Burns Woodward and his team in 1951. Cortisone is a highly complex steroid hormone used to treat inflammation, arthritis, and adrenal insufficiency. Once the synthesis of cortisone was understood, the synthesis of other hormones followed, which opened the path to the production of the pill. Organometallic catalysis is the preferred method of synthesis of sensitive molecular structures in modern day. As one proceeds from left to right in its periodic table, transition metals progress, having filled the d orbitals in the corresponding n-1 level before filling the s orbitals in the n level. Thus, palladium has the unique configuration 4d10 5s0. Because the 5s orbital is empty and relatively close in energy to the filled 4d orbitals, palladium can easily promote electrons into the 5s or 5p orbitals. This allows it to undergo the oxidative addition. where it donates electron density into the sigma antibonding orbitals, sigma star, of a carbon-halogen bond. It can donate electrons from its d orbitals into the empty antibonding p star, orbitals of unsaturated ligands, like alkenes or phosphines as well. Palladium allows for a level of electronic surgical precision, and this feature in turn is what allows pharmaceutical companies to synthesize drugs with complex multi-ring structures, the kind used in modern targeted cancer therapies, in a single high-yield process, usually at room or mild temperatures. In principle, an organohalide reacts with a boronic acid to form a new carbon-carbon bond, as in this example of the synthesis of Montelukast, singular, a medication for the treatment of asthma and allergic rhinitis. Act 9. A. A cultural and industrial revolution. Benzene, aniline, and phenol, all extracted from the once worthless coal tar sludge, became the structural building blocks of two massive multi-million-dollar global industries. William Henry Perkin could never have foreseen the tectonic cultural and medical shifts he set in motion. The synthetic dye boom occurred at the absolute zenith of the British Industrial Revolution, which was built on textiles. But by the 1890s, leadership shifted dramatically to Germany. Legendary corporate giants that we instantly associate with global healthcare today, Bayer, Ciba, Sandoz, now Novartis, and Hoechst, now Sanofi, were all originally founded as humble chemical dye-producing enterprises. By the late 1800s, these companies employed massive, unprecedented armies of industrial chemists. A profound symbiotic relationship developed with academia. Industrial profits funded basic research in synthetic methodologies, while academic tool building pushed industrial yields to new heights. These massive enterprises standardized methods of rigorous research, compound analysis, and structural quality control that had never existed in human history. Act 9. B. The Metamorphosis. As the mid-20th century approached, the Wild West era of medicine had to end. For decades, drugs were sold as unverified patent elixirs, with secret ingredients and fraudulent claims. In fact, even Coca-Cola famously began its life as one of these medicinal elixirs. Drug discovery was entirely ad hoc. Chemists simply synthesized thousands of random paths and tried them out blindly. But following a series of devastating international public health disasters involving tainted manufacturing, fraudulent data, and dangerous clinical malpractice, governments stepped in with absolute regulatory force. This intervention triggered the final cultural evolution of the pharmaceutical industry, the creation of strict mandatory global standards that govern every single step of modern drug development today. GLP, good laboratory practice, governs the initial research phase. It mandates strict standard operating procedures, SOPs, dictates rigorous personnel qualifications, requires an independent quality assurance department, and enforces ironclad data integrity to ensure every single scientific result is entirely traceable. GMP, good manufacturing practice, governs the actual factory floor. It demands ultra-strict cleanroom environments, mandates continuous process validation to prove that every run yields a drug of identical strength and purity, and enforces total batch records traceability. It ensures that an individual bottle of medicine bought anywhere on Earth can be traced backward to the exact machine and raw materials used to make it. GCP, good clinical practice, the ultimate international ethical and quality standard for designing, conducting, auditing, and analyzing clinical trials involving human subjects, ensuring safety, rights, and scientific validity above all else. Epilogue. It is one of history's greatest paradoxes. Humans set out to conquer the fleeting world of vanity and fashion, to make cheaper purples, brighter pinks, and richer greens to adorn the high societies of the industrial world. But in doing so, they unlock the secret geometry of carbon. The path walked by young William Henry Perkin through the sticky, foul-smelling coal tar did not just lead to a rainbow of textiles. It forced our civilization to master the molecular universe, giving rise to the very tools, reactions, and rigorous laws that defend human life today. The future holds faster drug development and testing cycles. New approaches like click chemistry, which puts great emphasis on efficiency and simplicity, ease of purification and speed, or new technologies like AI and machine learning, which allow the chemist to use deep learning algorithms that predict protein folding, such as AlphaFold, and generate entirely novel chemical architectures optimized for specific therapeutic targets, reducing early-stage discovery timelines from years to weeks. Thank you for listening to Chemistry Forging Civilizations. Join us next time as we explore the next molecule that reshaped our world. Until then, keep looking at the transformations around you. Give us a thumb up and subscribe for more chemistry that forges civilizations.